All right, how are we doing, everybody? Welcome back to my channel. Don't forget to hit the subscribe button.
Thumbs up.
What's that?
100 subscriber special.
Yeah, again, if I get to 100 subscribers, we're going to do a special giveaway. Food party. Food party.
Burrito party.
Burrito.
I like burritos.
It's 7:45 in the morning.
Breakfast
Breakfast
burritos.
burritos.
You know.
Class trip. Class trip. Yeah. Ooh, class trip to Taco Bell.
We'll do the match for taxes.
But it's food. All right. So again, like I was saying a little bit ago, today what we're going to look at is what are the unique properties that logarithms have? How do we operate with logarithms? Okay. Because logarithms are exponents, right? We learned yesterday that a logarithm is equal to the exponent, right? So that must mean they must have some special properties, just like exponents do. Right? Just like the properties of exponents do. Okay? So they're going to be tied in. We're going to talk about them throughout. Think about the properties of exponents. What do we do if I have something like this? What would the power be? X to the 8th, right? If I've got x to the 6th over x to the 2nd, what would the power be? X to the 4th, right? We would subtract powers. If I've got x to the 7th squared, what would the power be? X to the 14th, right? So exponents have unique properties with them. Logarithms will also share those unique properties, just in a really interesting way. Okay. Remember that to foreshadowing there. Remember that to multiply with like bases, I add exponents, right? To multiply with like bases, I would add exponents. You know this already. You learned this probably like in 8th grade, 7th grade maybe, I don't know. To take multiplication with like bases, you add exponents. B to the m plus b to the n is equal to b to the m plus n. Okay, so I'm saying if I've got like bases, I am doing addition of exponents. Aren't logarithms equal to exponents? Yes? Logarithms are exponents. So I must have to do something with logarithms. Oh, look at this. Go ahead and write this down here. This is the multiplication property of logarithms. You can write down in words what it is too. By all means, go for that if you'd like to. But the thing that I think is important is the algebraic definition. The logarithm of a product is equal to the sum of the logarithms of its factors. So multiplication, this is basically what this thing is saying. Multiplication is addition. Just like exponents, right? Multiplication with like bases was addition within the exponents. And if logarithms are exponents, we must be adding the logs together. Log base b of m times n is equal to log base b of m plus log base b of n. You know, this example that they give in the middle is really silly, because does it do anything? No. Log base 3 of 1,000. I mean, it separates it, sure. It shows the property, I guess. But log base 3 of 1,000, think about factors of 1,000. Isn't that like 10 times 100? Right? 1,000 is 10 times 100. There's a lot of other factors that we could have done as well. But it's 10 times 100. So what we could do, since it's multiplication within the log, I can separate it out and do addition of those two pieces, separating out the logs. Log base 3 of 10 plus log base 3 of 100. Now, does that simplify anything? Like, can you actually take log base 3 of 10? Like, think about that mentally. What is that asking you? 3 to the what power is 10? 3 to the 2nd is 9, so it's like 3 to the 2.1 or something like that. It doesn't make sense. Why would you even need to do that? Well, I'll talk about cases why you need to do this and why this is useful. This is especially useful when you're solving logarithmic equations and solving exponential equations. All right, so this is the product property. Oops, went way too far. Now you're going to see in the directions on both the homework and the quizzes and the tests, you're going to see this direction: express as a single logarithm, then simplify. The reason I'm asking you to do that is because I'm asking you to show the property. Show the property that I'm asking, and then get it down to just a single number. Then evaluate. Okay? Then evaluate. Express as a single logarithm, then simplify. Because the thing here is I could evaluate these two separately, but I want to express it as a single logarithm, and then simplify. Okay, so addition of logs means what in the log? Multiplication, right? So this means log base 5. Now, it's something that I neglected to say, but did the bases change at all? Look, base B, base B, base B. Do the bases change at all? No. Just like up here, when I was working with my x's, does my x term change at all? Does my base change at all? Never change the base. So if I've got log base 5 of 625 plus log base 5 of 25, that's equivalent to log base 5 of 625 times 25, whatever that is. Right? So we go in to our calculators, we say, okay, what is 625 times 25? 15,625. Log base 5 of 15,625. Okay, now what we say is, okay, what does that evaluate to, right? Think about what the log means. That means 5 to the what power is this big number? 5 to the what power? Well, it's probably not 5 to the third. Maybe 5 to the fourth? Nope, not yet. 5 to the fifth? Nope, not yet. 5 to the sixth? Bingo. So this is equivalent to 6. That's equal to 6. So what I'm going to ask you on the quiz and in the homework and stuff, express as a single logarithm. That's my answer for the problem of express as a single logarithm. Then simplify. That's the answer for simplify. There's going to have 2 answer blanks on it. Why am I asking you to do that? Well, what's log base 5 of 625? 4, right? Isn't log base 5 of 625 4? What's log base 5 of 25? 2. 5 squared is 25, right? What's 4 plus 2? 6. So I need you to express it as a single logarithm, then simplify. Express as a single log, then simplify. All right. This one you cannot evaluate ahead of time. Okay, go ahead and do this one. Okay, what does this simplify to as a single logarithm? Log base 6 of 36. Right? So that's my answer for express as a single log. What does this simplify into? What is log base 6 of 36? 2, right? 6 squared is 36. So that's what it simplifies into. Yes?
How do you know if you can make like this?
Like this. Can I evaluate something like this? Like 6 to the what power is 4? All right, that doesn't make sense. I can't, do that. Make sense? It actually, like, isn't this something like 6 to the what? 6 to the first power is 6, right? So it's something just a little below 1, maybe like 0.7 or something like that. Think about this, 6 to the what power is 9, something a little bit above 1, right? Maybe like 1.3, set, adding together. It should make sense. 0.7. Go ahead and try that one. Okay, what is it as a single logarithm? Log base 1/3 of what? Of 3, right? Okay. Now, be careful with this one. That's a single log. If you need to transfer it into exponential, think about it as 1/3 to the what is 3. What is that? -1. -1. Again, people always think fractions means there's going to be like a decimal or I don't know. No, it's just a negative number. Questions about that? Okay, so multiplication inside the log means addition of the logs. Okay. We remember the division property, the quotient property, right? We talked about this a second ago. X to the 5th divided by x to the 2nd would be x to the 3rd, right? We subtract. So division means subtraction. Division means subtraction. Okay, so how does that relate to our logarithms? Division inside the log means subtraction of the logs. Again, the base does not change. You have to have like bases to be able to compute these things. If I tried to say, log base 2 of 7 plus log base 3 of 8, nothing to it, right? That's like saying x to the 3rd times y to the 3rd. You can't like make that xy to the 9th or something like that, xy to the 6th or whatever. Have a look at what that says below, man. My notes are speaking of. Gotta have the same base to be simplified. So log base b of m divided by n is equal to log base b of m minus log base b of n. Division inside the log means subtraction of the logs. Because again, when I was looking at exponents, as long as they were the same base, if you had one divided by the other, a base divided by base, we could say power minus power, right? Exponent minus exponent. And if logarithms are equal to exponents, we are going to subtract the logarithms from one another. Log base b of m divided by log base b of m divided by n is equal to log base b of m minus log base b of n. Again, the example that they give you in the middle is silly. Log base 5 of 16 over 2. Why didn't we just say 8? I don't know. Log base 5 of 16 over 2. You could split that up to say log base 5 of 16 minus log base 5 of 2. But does that do anything for us? No. 5 to the what power is 16? It's some decimal. Somewhere between 1 and 2. All right. So again, the directions are the same. Express as a single logarithm, then simplify. This is another one that we would not be able to simplify ahead of time. We have to express it as a single logarithm and then simplify. So I've got log base 5 of 100 minus log base 5 of 4. That just simply turns into log base 5 of 100 divided by 4, which is 25. That's single log. Okay, what is log base 5 of 25? 2. that make sense? That's how that works. Okay, let's try another one here. Go ahead and do that one. That one's pretty simple. That one we could simplify ahead of time, but again, express it as a single log, then simplify. What does this simplify all the way down to? What does this simplify all the way down to? What's my final answer? 1, right? 1. Because this is log base 7 of 49 over 7, which is 7. And that's one of the properties that we learned yesterday, right? Log base b of b is always 1. 7 to the what power is 7? 1. So again, that's expressed as a single log. That is my simplify, my answer. Again, I could have simplified this ahead of time. What is log base 7 of 49? 2. What is log base 7 of 7? 1. So 2 minus 1 gives me my 1. Okay? Now, we saw, oops, apparently I don't have the exponent there. We saw earlier on today, x to the, I don't know, I think I said x to the 7th raised to the 2nd power, right? Whenever you have a power raised to another power, what's the operation in there? Multiplication. So a power raised to another power is multiplication. Okay. So that means, let me make this a little bit bigger for you. Sometimes it's hard to see the letters. Log base b of a to the p is equal to p times log base b of a. Okay, so again, it says if you've got an exponent within a log, and you know, I've been saying all along, logarithms are exponents, right? So this is like saying an exponent with an exponent with an exponent, or a power of a power. That signifies multiplication. So if you've got an exponent within a log, that's like saying a power on a power, an exponent on an exponent. So what you can do with that exponent, if it helps you at all, is bring it around in front. That, whatever that power is, it goes in front and multiplies to it. Now, why is that property there? I like to think about this. If I have log base, log base b of a to the 3rd power, right? Log base b of a to the 3rd power. Isn't this like saying log base b of a times log base b of a times, I'm sorry, no good. A to the 3rd power. Right? Isn't that like saying that? So what does multiplication mean? Multiplication inside the log means what of the logs? Addition of the logs. So this would be log base b of a plus log base b of a plus log base b of a. How many of those do I have? 3 log base b of a's. That's why this property holds. You see that? I can bring that number around in front. It's just basically like doing all that work ahead of time for you. Right? You just have to know that that number comes back around in front. All right. Everybody always says, does that say plog? Log. All right, so we got log base 2 of 32 raised to the 6th power. See, like I'm thinking, I don't really want to do 32 to the 6th power, right? But what I can do what I can do, I mean, it's possible. 32 6 power is just a really big number. What I can do is bring that 6 around front and multiply. 6 times log base 2 of 32. What is log base 2 of 32? Well, 2 to the third is 8, right? So 2 to the fourth would be 16. 2 to the fifth is 32. So 5. That's expressed as a single log. So this would evaluate to be 6 times 5, or 30. Okay, take a look here. 32 to the 6th power is this big number, right? Guess what? 2 to the 30th power is the exact same thing, right? So I could have evaluated without bringing that power in front. It just makes it a little bit simpler for us. Okay, let's take the second one here. Oh, first off, what's my base on my log? 10, right? It's common log, log base 10. So 4 times log of 10, log base 10 of 10. What is log base 10 of 10? 1. So this would be 4 times 1, or just 4. Okay, that's a unique property, right? If you ever have this, and we'll write it down, I think it'll summarize this in a second here, yeah. If you ever have this where you have the same base, log base b of b to the exponent, that actually cancels out. Why does that cancel out? Because just like this turns into 1 right here, it's always going to be that number times 1. So in essence, we could take a shortcut and say cancel, leaving just the 4. Okay. Go ahead and do that one real quick. So again, that 2 comes around front, multiplies out front, becomes 2 times log base 5 of 25. What is log base 5 of 25? 2. So this turns into 2 times 2, or just 4. Does that make sense? Okay. So those special properties that we were talking about, ones that undo each other. Again, I would write them down here. If you ever have log base b of b to the x, which is like we just had with that log base 10 of 10 to the 4th. Log base b of b to the x cancels. Log base b of b cancels, leaving just an x. Why? Because that x would come around in front, and log base b of b would turn into 1, so it'd be like x times 1, or just x. Likewise, if you take b to the log base b of x, b to the log base b of x, those would also cancel. If you've got a log base and an exponent base that are the same, they're acting on each other, they cancel out because, again, they are inverses. They undo each other. Why does that second property hold? That's an interesting one to point out. B to the log base b of x is equal to x. It's interesting to see here, if I turn this equation, this is an exponential equation, right? I've got b to the something equals x. If I turn this equation into logarithmic, turn this exponential equation into logarithmic, I would say log base b of x is equal to log base b of x. Is that interesting? Right? You know, like if I didn't know this term, like what this was, like if I was trying to figure out what this property really was, I could say this, you know, b to the what, right? And then you could just logically assume log base b of what is equal to log base b of x? Well, that must be an x, right? For that statement to be equivalent, that must be an x. All right. So pretty simple here. What is log base 3 of 3 to the 11th power? 11, right? Cancel, that becomes 11. What is, well, this one is not written in that form, but watch what we could do. Can I make this a base of 3? 3 to the what power is 81? 3 to the third is 27, so 3 to the fourth is 81, right? Isn't 81 just log base 3, sorry, isn't 81 just 3 to the fourth? So I can rewrite this as log base 3 of 3 to the fourth. My answer is just 4 then. Could I have evaluated that? Could I have said, what is log base 3 of 81? And just figured out, well, 3 to the fourth power is 81, so it's just 4? Yeah. But again, learning these tools will help us when we start solving equations. And then likewise here, 5 to the log base 5 of 10. Cancel, just becomes 10. 2 to the log base 2 of 8x. Same base as exponent base. Cancels just to become 8x. That's a unique property where you have an exponent, a log within an exponent that are both of the same base. You can cancel them out. Because again, they undo each other. Now, we learned yesterday that a lot of our calculators, you can change the base. But a lot of the calculators that we used to have does not change, they don't allow you to change the base of the logarithm. So here's what you can do. Now, why is this useful? Because guess what? On those little red calculators, they also have a log button. The little red calculators have a log button. But do they have a change of base button? No. So if you're ever stuck with one of those calculators, you can use this property. It's called the change of base formula. Okay? Let's write that one down. It's called the change of base formula. This was extremely useful to us a couple of years ago because your calculators had not come out with that change of base function, right? So you could not physically change your base. No one could on any calculator. So this was the only way around calculating logs that didn't come out as nice mental math logs. You may be thinking to yourself, well, how did they do this before our nice fancy calculators then? And how did we do this before this formula? Like, how were we able to do this? Well, it's interesting that you ask, even though you didn't ask. Pull out my, where is it? Yeah, pull out my grandfather's trigonometry book from the Navy, George Labber. And you look in the back. This is a trigonometry book even, and there's a whole bunch of trigonometry tables, right? And look, including that are logarithm tables. So you actually had to find in the table logarithms, right? You had to say, okay, what is log base 6 of 4, right? That's one that's not easily calculatable, right? And you had to like go through, okay, log base, where's my 6 table? And we had to say log base 6 of 4 and had to figure out where the decimal was just by looking it up in a table. You know, this is the textbook, right? This is the textbook. The length of that, that's all the tables within the textbook. Yikes. Crazy, right? Oh no, it's Mrs. Brown. Oh my gosh, I forgot to mark him absent. Oh, I'm so sorry. I marked Camille absent, and I did not mark Batchik absent. I'm so sorry. Oh my gosh, I'm so sorry. I saw. And that's recorded. Oh, geez, great.
Everyone on YouTube will know.
Exposed.
Exposed.
That's what you should name the video.
Yeah, like I'll put it in. You won't believe what happens during Islamic first period class.
Not the
Please.
game.
That's how you get them. Yeah, that's how I get them. And then that. I'm really smart and not really
You should
smart.
also call the snow day today, just so we have a recording that there's not gonna be a snow day tomorrow.
There's not going to be, according to me, there's not going to be a snow day tomorrow.
Okay, we have that recording now, so when it happens.
So when it happens, you come back and sue me. All right. So what does this change of base formula actually do for us? Well, what can your, if you didn't use your log base function, change of base function in there. If I was just using a little red calculator, it has that log button on it. What does that log button actually calculate in? What base? Base 10, right? This change of base formula allows you to change anything into base 10. It actually allows you to change it into base whatever you want. This is really cool. If you've got log base b of x, right? Say log base 6 of 4. 6 to the what power is 4? I don't know, some decimal. Something less than 1, right? I can change that base into whatever I want. I can pick anything that I want. The most useful one is probably base 10 because your calculators compute in base 10. So what I can say is log base 10 of 4 divided by log base 10 of 6. I can change the base into whatever the heck I want. I could say log base 1,000,000 of 4 divided by log base 1,000,000 of 6. I don't know why I'd do that, but I could. So the nice thing about that is, see, I don't have my fancy log base function on here. I can now go in and say log of 4 divided by, I should end my parentheses, divided by log, I guess I don't need that parentheses in the first one, log of 6. And guess what? It's 0.77370056, right? Thank you, 145. I don't know why I went that long and didn't cut off the 145. And before these calculators would do that, you would have to go and look it up in a table and see what it would be. Just like, sine, cosine, and tangent values. Before your calculators, they would have to go in and find them in tables. Okay, all right. So go ahead and evaluate these using the change of base formula. The change of base formula. So you're going to have to do it in your calculators. And you fancy people could just technically use the log base function in your calculator, but I can't do that. So the original base always goes into the denominator. Don't make it log of 32 divided by log of 8. It's log of 8 divided by log of 32. 0.6. Do you guys get the same thing? Do you guys want to see something cool?
Yeah.
What if I had changed this into base 2? Because I could change it into whatever base I want, right? Well, this would have been log base 2 of 8 divided by log base 2 of 32. Guys, what is log base 2 of 8? 3. What is log base 2 of 32? 5. What is 3/5?
Oh.
0.6, right?
Oh.
So I can change the base into whatever I want. It just happened that 2 was a nice base for both 8 and 32. Okay, that doesn't always work like that. Log base 9 of 27. This one almost looks like we should be able to do it without our calculators, but it's a 9, not a 3. I need log base 9. 9 to the what power is 27? So we would take log of 27 divided by log of 9, and we get 1.5. And just for good measure, here's the last one that we got. Oh, that's Weird. Okay. Log base 1/2 of 10. So we would say log of 10 divided by log of 0.5. And we get, woo, that's a funky one. -3, ooh, a negative?
See the excitement.
Why is it negative?
Oh, because it's a fraction.
Because it's a fraction. So this would be log of 10 divided by log of 1/2. That gives me -3.32. Okay, so long everybody out there on YouTube world.
Subscribe and leave a like. Yes.
You heard Cooper.
I hope they did.